What I want to talk about is how I perceive the learning theory. That will be my point of view, probably, which is not shared by most of the young people here, because they're obsessed with deep neural networks, and I'm very suspicious of big neural networks, and I'm going to tell you why. So first of all, the mathematical learning theory provides justification for machine learning algorithms, and practically people prove theorems about this and consider what is happening in this case and that case. So the classical case which is considered is the case when we have underfitting approximations, which means that we have much less parameters than data. So when we have data, we don't, at least that was the point of view before, you don't want to put more parameters in your approximation tool in order to fit the data. Because obviously you will overfit the data. You'll have too many possibilities of a failure. So because you have a big set of functions which that can satisfy the data, can fit the data exactly. So that is why, that was the classical theory, was that we have to underfit. And I'll show you some theorems, and based on these theorems, it seems like if we have n data points, the best underfitting is by n divided by log n. So that means a little bit less parameters. And then, however, when the deep neural networks arrived, in a sense, neural networks were well known even, say, 40 years ago, and people were using them for different approximations. At that point, there was no fast algorithm which to realize a really big neural network with a lot of neurons. Usually, neural networks about less than 100 neurons were applied because it was very computationally intensive to find such a neural network. Now the concept was changed with the stochastic gradient descent. People say, okay, we don't want to find the neural network which does the best job in approximating. We just can find some neural networks which give us close solution. And actually, amazingly, that helps if you have a minimization problem that has more than one local minimum. And with the stochastic process, you can eventually jump from one place to another and eventually find this minimum which is good for you. However, that comes with the overfitting. And overfitting means we have several possible solutions, actually infinitely many usually, some of which may be awful, maybe something we really don't want. And that is why people take care of it in some ways. The classical ways, which is actually employed, and we have Stan Osher here who will say, okay, we have to have regularized minimization, especially if it is a TV minimization, that would be the best possible. I'm kidding, of course. But that is actually, we need a penalty term to do something. This is the explicit way of making the minimization process proper. However, most of the available algorithms are implicit. People design algorithms and then they kind of put inside of the algorithm, in the minimization procedure, some conditions on the way this minimization process is going, and then based on this condition they say, okay, we achieve our goal. We have a minimization at the end. This is not always sure, and people have different ways of guiding the minimization procedure. One of them is, say, adversarial neural networks. The other one is midfield games, which actually are played in order to guide this process. So now I will go over two of the basic learning problems from the classical point of view. This is the regression and classification. And there is a third one, which is density estimation, which is a little bit more difficult to solve and actually requires much more data to solve this consistently. But I can comment on that also. So let's consider the problem. We have some finite domain in d-dimensional space. We have a subset of the interval, so we have a function from x to y, actually a process from x to y, and then we assume that we have a probability measure which is placed on the product of these two spaces. That actually, learning this probability measure would be density estimation. But we want to have something small. This is the regression function, and the regression function is nothing else but taking a specific x and consider all the y's which are in this probability distribution. So for fixed x in x cross y space, we have a lot of possibilities of the y's. We have different probabilities for each of the y's, and we integrate all of this according to the probability measure of y given x. And then that's the conditional probability of the space y. And then we receive a number which would be the value of the function f rho. This is unique number. This is actually the average value according to this probability distribution. And then the goal is, when we have the data, to find this function. This is very often the way we want to understand what is going on. And to give you an example, we consider this probability measure, which is kind of, it is continuous here for each y. This is the axis, and the y is this interval. For each y, we have different possibilities here on the left. On the right, we have only two possibilities. One is to have either this value or this value with different probabilities, of course. And because of different probabilities, we have this kind of average value. So this is the regression function, is this red one. And we want to approximate it. What will happen? So I put here 1,000 points. This is randomly drawn from this probability distribution. As you can see, they kind of go left and right. And we want to calculate based on some sample points to calculate this function. So how we do the empirical solution? It's very simple. We assume to have some hypothesis class. That means we define a class. Yes?
I have a question about the previous graph. Why was the regression function on the right half? Why is it so close to the upper diagonal? That's just to understand this.
Which?
On the right half.
Yeah, why?
This one?
Yeah, it's so close to the upper diagonal. So
why it is supposed to be upper diagonal?
No, it's so close to it. On the left, that's more like.
No, these are different probabilities for these points, and this is simply the average.
Weighted average, weighted by.
It is weighted by the probabilities. Of course, these probabilities here are equal, but this one eventually is higher than that one. This is just to compose a function which looks like that. It's not, the intensity here is supposed to show what is the probability density of on this line and on that line, and this is what is happening. So That is just the calculation. Okay, this one, sorry.
I was going to say, I thought you wanted to illustrate the fact that this regression function is the same for very different types of measures. So,
Yes, of course.
but then it doesn't look the same, which is good.
No, it is not the same from both sides. This is not the same from this one and this one.
I thought you wanted to say that it's the same.
No, it's not the same. It's usually this is kind of taken. I did that several years ago. I can't even remember what are the probabilities, but just wanted to have some nice function which is not flat completely. So what is the usual procedure? Let's imagine here that we have different intervals, and each interval we have, say, we can say we have 10 parameters on each of this interval. We consider all the points, we average them, and consider some average value, and this is our approximation tool, piecewise constant approximation. We can do several different things. We can do, for the hypothesis class, some neural network and something else, and combine it. The thing is to see what happens if we vary the number n of the parameters and do just the possible minimization, which minimization in this case, we are having least square minimization of all the points according to the parameters. As I said, if we have a piecewise constant approximation, that would be just the average of all the y values which are in that interval. And then what is happening if we consider a general hypothesis class, general H? We have that from this class. This is class of functions, several different functions. We know how we can approximate the function f rho if we are given the function. And we have the approximation with that is called bias. And this is something which we can estimate if we know the smoothness of the function usually, and we know what is the class. So that is the approximation, say approximation by polynomials, approximation by wavelets, or approximation of something else. We know when we're choosing the class. We even have for deep neural networks, we know what approximation they can provide for different types of functions. Class of functions, not specific functions. But then we have something which is called variance. What is the variance? This is how actually when you have this approximation of fh, if you have the same function but different drawings according to this probability measure, we can receive different realizations fz of this function. So in this case, if you increase the number of parameters, you will have more variability here, and this one would increase if you have more parameters, and this one will decrease, of course, because we'll have a better approximation. So we want to have a balance between the two. And that is why I said in the classical settings, we want to underfit. Why? Because if we overfit, that would be 0. We'll have a perfect function, but that one eventually will be very big. And now I want to draw different. As I said, we do piecewise constant approximation. These are 1 million samples, so big enough number. We have 16 parameters. That means we subdivide the interval into 16 subintervals and make the piecewise constant approximation. Okay, this is underfitting. Obviously, we need to put a little bit more parameters. And if we have 64 parameters, we already see that it's a relatively good fit. Is that the best fit? No, this one is even better. But if you compare here, you see that kind of the approximation is locally monotone almost everywhere eventually, except here, but it's kind of following the shape of the curve. Here, although it's much better approximation than before, we see some small artifacts which appear here and there simply because we have statistical data. We have drawn this million points, and then it turns out that they kind of vary from one to another, from the average position. And then if we go to 256 elements, we already overfit. So in several places, as you see, we are kind of away from this behavior we want. And then if we have 1024, which is kind of 1,000 times less than the number of points, we still we have a terrible approximation. Yeah.
Why is it better near zero, or at least on this upper slope?
Because from this side, yeah.
Take a measure and look at its marginal on the x-axis.
Yeah.
What does it look like?
No, but this is what is around zero. So around zero, we have a very small thing. Around the ends, we have very big variability. So that's why
your bias term is kind of much more relaxed around zero.
Yeah, that is why it is what is happening. So that is the severe overfitting, and we want to achieve an optimal balance between the bias and variance, and one way to do that is through adaptivity. So, and the algorithm should work without any a priori knowledge of the underlying probability distribution, and then we want to define the theoretical estimates for the performance. So the distribution-free approach is this is one of the basic books for at the beginning of learning theory, which actually describes all the processes and defines what is happening. I also want to say that probably the people who brought the attention to machine learning, and actually the mathematical theory to that, was Steve Smell, and mainly Steve Smell, but Cook and Smell paper is kind of the foundational paper which said what is there. Actually, what I will be talking about is some improvement which Ron DeVore with Gerard Ketcheran and Dominique Picard and Volodya Temlyakov have done, and we actually made several steps. This is opposite of the what we were doing there in using adaptive partitioning. We were trying to go away from the scheme. I think that strategically that was a wrong move, considering the developments of the deep neural networks. But it's a nice theory, and I want to say what it is in general. But as usual, this is the CART algorithm for the classification and regression trees. It is it is very old book, and then it considers tree structural splitting procedure, which means the following. You have your domain, usually it's high-dimensional domain. You start subdividing the domain, eventually by 2, because this is the easiest way, and you have a binary tree. And on this binary tree, you kind of, the splitting procedure could be different. You could decide based on the data how to split, but you also could have a procedure which is defined at the beginning. So you just split into two in some way. And after splitting the domain in several pieces, in each of the pieces you use your favorite approximation tool to approximate in this place what would be the function. So what was at that point? You consider the error of approximation, but you have a penalty which is related to the complexity of the tool you are using. So the bigger the complexity, the bigger the variance. So that's why you don't want to overfit. So that's why you kind of make a compromise between the error and the complexity. Actually, what turned out that if we consider this kind of the procedure, we kind of can incorporate the penalty in the procedure and stop at certain place. So basic thing is we do wavelet-like decomposition. I hope you have heard of the wavelets. If you haven't, this is simply decomposition of the function, multi-scale decomposition. So you start from the beginning with very coarse approximation. That means very low frequencies. Then you approximate the function, and then the remainder you use high frequencies approximations, and you kind of build a tree of the coefficients which are there, and you make the decompositions. This phi lambda, usually this is multi-scale structure, and the interesting part is that we don't have to know what are these functions, because they might be based on they should be based on the distribution of the points, so on the probability measure. But we can make an estimates of these numbers, and the thing that drives the procedure is we are taking all the big coefficients, and we are doing the approximation with these coefficients. So when doing that, we can prove some universal estimators. Here the universal is the important thing, because when you do the universal that means it is independent of the smoothness of the function we're approximating. So the function, we can assume that it is in some general class, but we don't know the smoothness of this class, the level of smoothness. It could be very smooth, it could be very rough, but we can use the same procedure regardless of what that is. And this universality is one of the most desired algorithms when you start approximating data. So and the result is basically the following. If we have here, it is formulated with an approximation class. The approximation class is made dependent of the dimension. That's why this D here. But basically, it says the following. If the probability of a failure, that means the error exceeds some number, which is fairly small number because it's m to some negative power, is very small. And or in expectation, that means this error is less than the square of the error is less than the square of this number. So and that's why say, okay, if we do this procedure, and this is kind of described in a sum, the most interesting part of it is that these coefficients, these varied coefficients which can be calculated, there are some certain ways of calculating, we know the threshold in advance without knowing what is the smoothness of the class. It seems that there is this universal threshold which is true for all the classes. And based on that, we can prove such an estimate. So that is kind of what is happening in regression.
Peter,
Can I ask a quick question here? So you talked about CART, and CART by nature gives you a connected tree, but wavelet thresholding may not give you a connected tree, I guess?
Yeah, it doesn't give you connected tree, but you can connect it. And if you are a certain smoothness class, that guarantees you that the additional connections are not much more than the whole thing. So that is a typical thing. So we just say that if you have certain number of the coefficients, and if you know that you have an epsilon extra smoothness of the function, then you can say that this connects everything. Yeah. So yeah, good question. Now I want to consider the classification. Classification is same thing as a regression. However, the Y space consists only with finite number of outputs, and here I'm considering the binary classification because this is kind of the simplest one, and everything can be considered binary classification because we can say, okay, we choose some class of functions, and we say, okay, we have a classification whether the object belongs to this class or not, and then do for all the classes. If we have 20 classes, we can do one by a time. It's bad for analyzing the algorithm, but at least theoretically we can make the binary classification the basic things. What is different between that, and actually let me say that in most of the cases when we consider classification, we practically can calculate the regression function, and based on the regression function, we can make certain decisions about the classification. However, the way we measure the error is different, because before we are doing classically L2 least squares error, we can go for some other errors, of course, but that is not. And then how. So what I'm going to talk about is the classical problem, and the classical problem is the following. We consider all the x's. We have the set of x's. This is kind of some domain omega. And we have in some part of the domain, we have that it belongs to our class, and some part it is not. And now we want to partition the domain in such a way to find a portion of this domain for which we can say that these are from our class, and for the others that they are not. Of course, we are not allowed to to subdivide the domain as much as we want. We kind of have to pace ourselves. We cannot involve too many degrees of freedom. So when we subdivide the domain, we have to say, okay, we have this number of partitions, and we want to work with them. So how that works? And then we said, okay, what is the measure of success? We have something which is called a risk, and the risk actually is the probability of a failure. So if we predict in some place that it would be from our class, but eventually we draw a point and it turns out not to be from our class, then we're failing this possibility. And failure could be all the times, because it could happen that for the same x we could have a positive or negative outcome. And of course we have to choose the way when the positive outcome is better than the negative. So that is why we have different formulas for the risk, and this is the probability that y equals +1 given x, and then there are simple formulas to say how that works, and then this is actually the most used formula. This is the C here is kind of the average of what is happening everywhere, and then eta is some function which is describing the difference here between the probabilities. Okay, so the base classifier is the ultimate best. This is the one which is, if eta is positive, that means we are in a good part. We predicted well. If it is negative, it is not. And then we have the base classifier, all the etas. Some people write it strictly positive, but the zero obviously doesn't make any change because it's 50-50. It's kind of this part of this constant C when we have that we have some probability of failure. So when we and the goal is to find this set. So and we want to approximate by another set, and this set should be from some family, and then we want to do approximation by the family. So how we do that? We say, what is the excess risk? Because we, as I said, we have some points in which we have always probability of some failure, and we want to kind of take this out. It is kind of unavoidable risk. This is the minimal risk here, which we have. And we want to see how our algorithm performs. So if we have some set omega, which we define, then to be our classifier, we want to know how much worse than this R we are doing. And then we have the excess risk would be our measure of success. And this is some way to say, okay, the excess risk, there are different ways to express it. And then to say, okay, what would be our goal to find a minimal excess risk. And that means if we're in the set F, one way is to calculate the argmax of this function eta. So the eta was the function between defined by the probabilities, and it is positive when we have it's more likely to be in the set than not. So and then we split actually this excess risk into two quantities that is similar to bias and variance. So that is the bias. So that means how well we can estimate the risk with the class F, and the other is the variability of F from. So to estimate it, I'll not go much, but talk much about this. But obviously, we have to design some procedure. In this case, the procedure is to start subdividing the set into several subsets and see what is happening. So use the data to tell us which of them should be put into our set omega and which should be put out, or eventually when we have something which is undecisive and we want to subdivide further. And this is based on several algorithms. I don't want to discuss, especially this is a little bit more theoretical here, but want to mention something which is the VC dimension. Probably, I don't know how many people know, but it is a very interesting way of classifying it. It's especially to say how good is this set F of possible partitions we want to consider. And this is like how the points can be shattered. Say if you have 3 points on the plane, you always can separate any subset of these points with a line. So if you want this to be from one side, this to be from the other, you can use this line, that line, and so on. However, if you have 4 points, you cannot do that. If you have that these two are in one class and these two are in the other class, then you cannot use a line to separate them. So that means the VC dimension is 3 in this case, and that means if we use a set of Fs of all half planes, regardless of how big is the set, it has a finite possibility to actually separate different points, which means that this is much more reliable measure to say whether some class of sets, a family of sets, is good or not. So that is used a lot, and then we can prove a theorem that eventually we have certain rate of convergence if we have a VC dimension V of the set F, and can eventually approximate that. So that is, so we can say something about performance of classifier. I probably should have not included that, but it is actually to calculate certain quantities based on this function eta, which helps us design the algorithms. But I want to point out about something else. So what is the important thing? So you have some probability distribution, you have some sets, you have some possibilities to be in one class on the other class. And then we want to say what actually makes the risk big and what makes the things bad. And these are two processes actually which act against each other. One process is we want to have this underlying function, this eta, to be as smooth as possible, because the smoother the function, the better we can approximate and everything else. But there is something like this, that when we have the risk set, so if we have, say, this is ours, okay, let me draw. Imagine that you have that this is from your set and this is not from your set. So what would you prefer to minimize the risk? To have a function like this, which is smooth, and then this is the decision boundary, and you decide that this is where you cut, so that would be your set and the other one would be the other one, or you want to have something like this, in which this decision boundary here, if we have some approximation, if you have real data, this decision could move left and right. Here, if it is very sharp, it will not. But if it is sharp, then what happens, we have that actually the norm, the smoothness norm of our function eta becomes worse. So these are two things which are fighting against each other. And in order to qualify that, so Tsibakov and actually first was a Massar that considered this for alpha equals 1, that is kind of considering how come this probability, this rho s, which is the probability of, I should have defined this somewhere. Okay, but that is the function which I was talking about. Is sharp enough or not? And Tsibakov has from any alpha between 0 and 1, and then we can classify, depending on what is the alpha, we could have some Q which gives us actually the smoothness class. So this is what turns out that the Tsibakov condition is equivalent to some quantity which we define here, the psi. Okay. Just in general, I want to say in general what is happening. So if we have a good empirical estimator for the family F can be designed, and then we can have certain error in estimating. We have some geometric conditions, which are the margin conditions for the sets. We have some smoothness conditions, and we have to balance them. So, and by choosing the appropriate VC dimension of V. And we can do this with model selection. And actually that is for designing the algorithms. What I probably don't want to convince you that this is an interesting area of research. What I want to convince you is that the problems when we consider classification are much deeper than just choosing deep neural networks and try to solve them. There are certain conditions which are designed to say, okay, whether this is a good function or a good approximation or a bad approximation, and this is what we have to consider if we want to solve a problem. And here that is the rate of performance, which says that how big could be the XX risk. So that is some number, which is log n, and is the number of the data points. And and here this is something interesting. That is why I put all these calculations from before. So this is considering a simple partition of the domain into subdomains. Actually, this is the done for a simple subdivision of the domain through the dyadic partition. So you have d-dimensional domain, and you consider it at the beginning to be a cube, and then you consider the partition into 2 to the d cubes, and consider this process, and then you choose the subcubes depending on how they are occupied with the data points, whether to go for one direction or the other one, and also to consider whether you subdivide further, because sometimes you don't need to subdivide. You have 2 points to make a good decision. The interesting part of this is what is called decorated trees, which is to some extent what people can do with deep neural networks, actually adding additional layer on that. And this is the following procedure. So when you have a cube in which you have points, in this, instead of just calculating which is good, which is not, you could have a procedure to have a hyperplane to cut the cube into 2 subsets, one of which gives you the most from one class and the other the most from the other class. So you look for the best hyperplane. Computationally, that is not that bad, but that eventually can increase from 1, because this is 0, 1 here, this power. It can increase it to 2, because that is second order approximation, and that will give you much better performance, just for this simple trick. So, this is something, as I said, it is something which people from considering deep neural networks, they kind of include such tricks at some point for their algorithms, but they don't explicitly show them in a theoretical way. Okay, so I want to say what is, so learning a function, we want to have a theoretical viewpoint, and My take on this is the model class. We always have to look for a model class when we consider some process, and we cannot do some general approximation. We have to consider what the problem is. And then when we're doing that, we eventually can end up in the following theoretical setup. The theoretical setup is something like this. So we have the function f, we have some observation of it, we have some data, and then based on this data, we want to have the best solution, so to find the function which solves the problem. And that is typical for the deep neural network. So we have some data, we run some function and see what is happening. But then we need some condition for this. We need to say, okay, this cannot be all the possible functions, because if we overfit, that would be plenty of these functions. We say we want to restrict ourselves to some compact class. We want to make this class known and to be small enough, and then we say if we get a solution from that, this should be a good solution. And how we measure whether this is a good solution, we can consider all the functions from this class which satisfy the data, and say and make a ball around this function with our favorite distance measure. And then, depending on how big that ball is, we can say we are approximating well or we are not approximating well. Because if the ball is very big, that means probably something is wrong in choosing our class, because it gives you a very big ball. But if the ball is small, that means we're in business. We could choose any point from this ball, and that will give us a relatively good solution that is near optimal, because it would be at most twice bigger than the best one. So if we do that, we can talk about near optimal recovery. So if we have a class K star which satisfies the data, then choosing what we want to choose a solution which is near this radius. So this is called Chebyshev radius, and this is radius of the ball that gets all the solution. If we do that, we say, okay, that is our solution. This is what we can do with it. And then even if we have a point from this ball, which often is not possible, we can do that. So how we achieve this? We achieve it in the following way. We get our data set. Our data set, we assume here it's designed by linear functionals of our function f. We assume that this is the way we receive the data. And then based on that, we can analyze and say, okay, what we need some way to measure the distance. This is the space x. We need some functionals which should be from the dual space. And then we consider the class of all the functions which actually could have all the data sites which are coming from our function in the class. And we say if we're given a data set, we want to say how well we can approximate. And in general, how we do that, we have some measure of fitting the data. That means we're choosing a function g. We know this functional, so we can calculate what should be the data for the g. And we see how different is that from our actual data. And then we put some penalty on g. So if the g is a good function, if we like the function, you put a small penalty. If we don't like it, we put a big penalty. And that's the regular S minimization. Of course, we should put here L1, but... Or TV, yes. Or whatever we want. And why this setup is important? I want to say how we can say when we achieve our goal. We achieve our goal when we can find a point in our class such that it is close to the data and close to the data, and also it's not too far from what we have there. So not too far from what we have, and then we say that if we are able to choose that for each epsilon, we have convergence.
What is KW in this case?
Sorry?
What is KW?
KW is the subset of this class you have, which satisfies the data W. So that means you have the KW, it is, but epsilon is if you fuzzy the data a little bit with the epsilon.
The norm is not actually a norm, it's a pseudo-norm, which is exactly given by the L2 on the linear function.
Yeah, it should be just distance.
You take the map by linear functions to Rn, and then you...
Yeah. So let me, so the proximity condition is something which we say, okay, we can find some function g epsilon from x, where x is our general big space, and say that we have to be close to the data and not to and close to the to our class. So, and we do that, and then we have a theorem that if we satisfy the proximity condition, then we can make this difference small enough and eventually have a convergence result. Let me give you just an example of how what is difficult in this K, so how the things could go wrong. So you can consider the K to be the set of a lot of functions. This is the whole square, and then just a line here. So if you choose the W, the data points, to be here, this is just one point, but of course we cannot draw, then you have a lot of variability. You could have anything here. If we choose it here, you have no variability. What, however, it is happening when you have some process, if you are on the border between the two, then eventually could happen, because you have to fuzzy a little bit because these are data points. If you make it fuzzy here, you have that this Chebyshev radius will not increase much because it's already big. Here, however, the Chebyshev radius was 0, and if we expand it a little bit, it certainly jumps big. And then, depending on the epsilon, you can see that at the beginning we're at 0, and then when we expand the epsilon until we reach here, it kind of grows slowly and then certainly jumps. And this jump is actually the bad point for the approximation. So when we want to approximate, you don't want this to happen. Actually, what we're using is that when we're minimizing the problem, so when we decrease the epsilon, we will go to this regime at some point, regardless of what is the point. So we'll have the convergence anyway. So how to solve that? So we have some general class, and then you have K, and then we consider the general model when we measure the distance to K. This is very difficult because it's very difficult to analyze this, because usually that is calculating the distance is not very easy in practical problems. However, I want to emphasize that when we do this problem, we have one big advantage. We don't have any lambda here to play with. We just can say, if this is our loss function, and we have our favorite neural networks to minimize it and to solve the problem, then we're in business. We will solve. We can receive the result would be good eventually.
What do you mean we don't have any lambda?
There's implicitly lambda, right? Because the definition of the distance could be changed.
Yeah, the coefficient of the distance.
No, but the distance. Remember, I had this condition. Actually, we say we assume that this is kind of close, but regardless of.
So lambda, you mean the lambda would have been the coefficient of the distance?
Yeah. So it appears actually. Let me say where it appears. If you consider now, instead of considering a distance, you consider a norm, which is the usual way we solve the problem, then we have to put the mu because this norm could actually depend. We have to rescale, yes. And we have to find the mu. But of course, this problem is much easier to solve because we have a good solvers for this. For this, in general, we have no good solvers. Theoretically, we say this is good. We don't have to find the mu. But practically, if we want the algorithm to run fast, and we can receive that. So that is practically the theorem says that eventually when we get these parameters, okay, let me say what is the most important thing. So we have to choose a set of approximants, sigma, which you can think of deep neural networks. And then we have the condition that the distance between the class K and this sigma intersected with the K should be smaller than delta. That is one of the parameters, how close we can approximate. Neural networks are very good with that.
I don't understand what this means.
Sorry?
This means zero? I mean... sorry.
No, this is the distance between
Okay.
the K and the intersection. So it...
Your point is that there should be nothing in K that's very far from sigma.
Yes. When you choose the sigma, yeah. And then I want to mention that there is no intersection here. So because we are using, if we are using the distance, it is also more favorable in solving. But as I said, it is not. So when we're choosing that, then we can say, okay, if we have this condition for the set sigma, that is our neural network, then we know that if we drive the minimization process long enough, and we have this parameter mu, which is this here, should be small enough also, then we have that we can achieve with a constant which depends on mu. So we practically say how to choose mu in that case. Okay, now to say why neural networks are bad, why overfitting is bad without this additional term. So this is simple example. This is solving some differential equation, something like that. But we have the initial conditions. So we start minimization process, and we use stochastic gradient descent for, or maybe even gradient descent. I'm not so sure, because it's very simple. You don't need the stochasticity, and start from the zero approximation, and then eventually we drive it to the solution. Here, because we don't have a lot of points, it actually is a little bit away from it, but it's a fairly good approximation. It fits the data. The data are the black points. However, if we choose mu equals 0, that means nothing here, then we have all these jumps of the approximation. Why? Because actually the gradient descent, when we have no points somewhere, this cannot be taken away from 0 because there is no way to change on that interval. Nothing happens. So, and that is practically everybody observed in these adversarial neural networks when they kind of try to push the network to avoid this kind of stuff because it shows them that solution and say, okay, you have to push in this direction. Okay, now I have 10 minutes to give you something from electron microscopy. One of the things was already given by Paul Walsh. So he was talking what we have to do there, and I can say that, okay, in most of the cases when we have electron microscopy, we have to think about our models. Because if we don't follow the model well, then we probably cannot find a solution. And one of the things is how to model the data. So we say usually that the data is the true solution plus noise. So very often this is the model which is in the books and everybody considers that. However, in STEM, as Paul mentioned, this is, we have a lot of position noise, simply because everything could happen. And that's why we have to include it in the model. If we include it in the model, then what we're doing, we say, okay, let's, if we have this noise, let's try to evaluate this noise. Let's try to find actually what are these positions. Can we find it from just one data site? And amazingly, this is a yes, we can do something about it because we can use non-local means. We can do this PM3D algorithm, and then when we're doing that, we can kind of take out this bad noise eta. But the other way is to just take several micrographs of the same site and see whether they change or not. If we are able to do that, we can estimate this eta and then have much better results. So this is the picture I wanted to show you. This is the typical change of direction. So these are the directions. We have a general movement of the sample. We subtract this general movement and then consider what are the differences from that. And you can see that from different places they go to different positions. And then if you consider this small green square where all the displacements were in one direction, if you actually subtract the average movement, this is the average movement of the whole thing. If you subtract it, you can see that again, they move to all over the place. So that is the first thing in electron microscopy. What I think we have to do is to formulate the problem which can improve the results. The second thing I want to talk is about EDX. This is energy dispersive X-ray spectroscopy. What it is about, it is when the beam is disturbing the material, eventually it kicks some of the electrons. And these electrons, if some electron from the low orbit is kicked, some electron from the upper orbit wants to replace it, and it emits the X-ray, which has a very specific wavelength, which depends from the atom. So if you detect the wavelengths of these X-rays, then you can say which atoms are in this column, which is actually penetrated by the beam. So this is usually how that looks for 1 pixel. So this is data from Binev Sagi. So that is not too much. So this is one X-ray different cases. If we want to understand what is happening, okay, maybe that is too much. To say we have to consider what is the combined spectrogram for all possible pixels. So that means this is for an entire experiment. We consider what is there, and then we clearly can see that there are certain sites in which we have a lot of X-rays, and that eventually will tell us which is the element. Yes?
Why is this three-dimensional? So 37 times 200 times 103 pixels?
Yeah.
I would have expected 2 dimensions.
This is 3 dimensions because it has a tilt angle also. So that becomes much worse. And then when we want to process that, we actually have that in each place we have less than 700 X-rays out of 4,000 sites. So that means there are not very many. Yeah.
Does this include data where, like, you would, for instance, kick out an electron that's not deep, but like closer to the surface, and then get a different spectrum out of it, or does it not matter which electron?
It usually doesn't happen. We have some noise. Okay, let me consider the wrong way. Let me say, okay, if we consider this, there are some electrons which are actually behaving badly, and this is the background signal, which eventually happens in the events like the one you described.
But the transitions you observe, they basically like don't depend on what electrons being kicked out.
No, it depends.
Okay.
Because they are different. Each atom appears in different sites. So they say, I think this one and this one are titanium, so that is, they're repeating in different spectrum, but the spectrum is specific for specific events. So one atom could have several different events. And here we have, and then the interesting part, actually, I think Stan also worked with that. This is kind of the, if we want to have a decomposition but with positive constants, that becomes very interesting. So we want to decompose our spectrum on the background signal plus some of these bumps here, which we can model in a different way. We actually model this as an exponential function, but it appears that actually this is not exactly a Gaussian distribution. It's slightly different from Gaussian, and this sigma j should be adjusted if we want to perfect data. But eventually, for the purposes of what we are doing, this approximation seems to be good enough. And then if we calculate, the question is, what are the Cj? But we are not looking for the Cjs for the entire spectrum, which I said. We are looking at the Cjs for this or that or something of this. So what are the constants? And you can see that there is a lot of uncertainty, and the data is not very good. And then, so the thing is how to do that, what is the learning process? So that is what I said, that here we might consider a much more complicated model. But in general, what we want to do is to say, okay, we know the basic modes. We know the functions which are involved. Can we make a filter out of it? And what the filter should do, it should perform the best in expectation. So we consider some functions which are our probability distributions, and then we want to find a filters. That means these are the linear functionals, simply constants for different constants for each energy of the spectrum, which when we multiply the data by them will give us ideally 0 for all the other sites and 1 for the one we need. Of course, that never happens because the data is very, very bad. And in expectation, we have some variability of expectation. We have to adjust these constants eventually to make them all non-negative, and to make also that the sum satisfies. This is kind of the filters, so that is considered different sides. This is the kind of, it is rough because it might include something else. This is the background signal, and this is the bump, and there are several bumps sometimes, like here, and this is how the filters look like. And after doing that, we can calculate for each of the basic elements we consider what is the element map from particular point of view. So that these are pretty clean pictures out of it. Oh, and then the last thing I want to say is that sometimes it's good to have two different modes to connect. So that is something which is something synchronous data, which is the dark field imaging. This is the dark field imaging. This is the EDX imaging. And we kind of combined all the possible elements. We use the z-square effect, which means the dark field imaging, usually the correspondence between the way they appear in the dark field, the atoms is fairly close to the z-square, where z is the number of protons in the element, so the number of chemical element. But this should be multiplied by 1.7 because we don't observe all the electrons which are emitted. So, we consider this from EDX, which has much less data, which matches very well what is considered for the other, and that is kind of checking whether we have a good result or not. Okay, that's it.